4.1, inverse functions. So now that we've dealt with functions, we've dealt with a variety of different basic functions, we're going to look at inverse functions. And we've mentioned them off and on as we've dealt with the other things that we've looked at. First thing I want to talk about is one-to-one. So one-to-one functions. If you remember that when we first talked about functions, we started out with relations. And we said a relation just was something that gave you an x value and a corresponding y value, or an input and a corresponding output. Whereas a function was specific that for each input there could only be one possible output. But you could have multiple inputs going to the same output. That was allowed. And so we said when we were graphing that we could actually use the vertical line test to verify that there was nowhere in the function, well, in the graph I should say, that you could draw a vertical line that would pass through the graph or curve in more than one spot. So that what helped us to determine whether we had a function. So therefore, something like this is a function, passes the vertical line test. Something like this is a function. It passes the vertical line test. With one-to-one functions, it is just what it sounds like. It means that the inputs and the outputs are one-to-one. So it's taking the function definition and reversing it so that now each input can only have one possible output and each output can only have one possible input. So they are one-to-one. Each input has its own output and each output has its own input. There is no duplication or multiple inputs going to the same output anymore. So that's a one-to-one function. So in this case, a one-to-one function must not only pass the vertical line test, which says that for any input, there's only one output, but it must also be able to pass the horizontal line test, which tells you for any output, there's only one possible input. So that's where we look back at our graphs, which I just showed here, and we go, okay, this passes the vertical line test. I can't do any vertical lines that pass through it more than once. It passes a horizontal line test. That no matter where I draw a horizontal line, it only touches the graph in one spot. So this would be a one-to-one function. As opposed to this, which is a function, but clearly fails the horizontal line test. Therefore, it is not a one-to-one function. So basically, what we're saying is that if we have two inputs, A and B, that are not equal to one another, then f of A must not be equal to f of B. And the converse is also true. If f of A is not equal to f of B, then A must not be equal to B. So let's look at a couple functions by rules. So equations, I'm just going to grab a couple here. F of x is equal to negative 3x plus 7. And g of x is equal to the square root of 49 minus x squared. Now we're not going to look at restriction on these right now. Obviously, we know there have to be restrictions on this, because if the square root goes negative, then we can't allow that because this is an imaginary result. So that's not, so we're going to ignore that right now. We're just going to look at these and say, are they one-to-one or not? I look at the first one, f of x is equal to negative 3x plus 7. That's the equation for a line. And it's a line with a slope of negative 3. So therefore, it is not a horizontal line. It is not a vertical line. We've already defined these as functions, so we can say that it passes the vertical line test. But since this is a line that has a slope other than 0, then it also passes the horizontal line test. So, is this a function? Yes, it is. It is a function. Now, what about this one? Well, it is a function. The square root function is a function. But notice this 49 minus x squared. Remember that x squared, that's kind of what I drew initially, that little parabola, and said, this is not one-to-one. Well, that x squared becomes a problem because if I plug in 2 squared, then I've got 49 minus 4 gives us the square root of 45. Fine. But if I plug in negative 2 squared, that also gives me 4. So 49 minus 4 is 45, the square root of 45. So we've got a problem. Negative 2 and positive 2 both give us the same result. So no, that is not a one-to-one function. So why do we care about one-to-one functions? What's the use of them? Well, what's the name of the section? Inverse functions. For any one-to-one function, there is an associated inverse function that is also one-to-one. And if you remember when I first mentioned inverse functions, not in this video, but previously, I mentioned how they undid whatever the original function did. And that's what inverse functions do. They undo the original function. Well, how can I find out if two functions are inverses? And let me just do a notation here. If we have the function f of x, then f to the negative 1 of x stands for the inverse function of that. That's not the reciprocal of the function, that's f inverse of x. So they will reverse each other. So if I have g of x is equal to the inverse function of f of x, and I want to see if two functions are inverses, then I can use composition. It's one of the last things we covered in the last section. So f of g of x will be equal to x, and g of f of x will also be equal to x. Remember, I said that they undo each other. Division is the inverse of multiplication. If I multiply by a number, it changes. If I divide by that same number, I end up back where I started. And that's really what we're saying with inverse functions, that the one undoes the other. So if I take the composition of f and g of x, I'm going to get x back because g of x is going to affect that original x value, and then f of x is going to turn it back into the original one. It's going to undo it. And the same thing the opposite direction. So if we have two functions and we want to see if they're inverses of one another, we can just find the composition both ways And if they both yield x, then they are inverse functions. So let's look at some functions and see if they're inverses. F of x is equal to x over 2, and g of x is equal to 2x. Now, from what I just said, you should go, those are inverses, Mr. Davis. Well, of course they are. Well, let's take a look and see. So if I go f of g of x, that means I take g of x, this 2x, and plug it in place of x. So 2x over 2 is equal to x. And yes, that works. We have to go the other way. G of f of x is equal to, now we're going to plug x over 2 in place of x and g of x. So we have 2 times x over 2, which is equal to x. And yes, they are inverses. Should put a s in there because they're both inverses of one another. And that's how we verify whether two functions are inverses or not. We can plug it in and see. So using composition. Let's see if I have one that's a little more complicated than that. Let's say we have f of x is equal to 2x plus 5, and g of x is equal to 1/2 x minus 5. So we have these two functions, and we want to find out, are they inverse functions or not? So start out with f of g of x. So we're going to take 1/2 x minus 5 and plug it in place of x here. So that's 2 times 1/2 x minus 5 plus 5 is equal to, distribute the 2 through. 2 times 1/2 is 1, so that gives us x. 2 times -5 is -10, plus 5 is equal to x minus 5. Well, guess what? That failed the test. So no, these are not inverses of each other. But that does lead to the question, it's one thing to be able to test and determine if two things are inverses of each other, and this looked like it might be, right? 2x plus 5, 1/2 x minus 5. We know that multiplication is the inverse of division. It undoes it. We know that addition is the inverse of subtraction. It undoes it. So you would think that, but no, we end up with a problem here. So it doesn't do what we would hope. But that does lead to the question, let's say we have the function f of x equal to 2x plus 5, and I want to find its inverse. Well, what am I going to do? Simply, what I'm going to do is I'm going to turn f of x into y. Because remember, f of x is just another way of saying y, the output, is equal to 2x plus 5. Then, I'm going to swap the input and the output. Because remember, the purpose of an inverse function is to undo what was done. So I'm going to make it so the input now becomes the output, and the output now becomes the input. So x is equal to 2y plus 5. I'm just swapping x and y. That's all I'm doing there. And now I'm going to solve for y. So I'm going to subtract 5 from both sides. X minus 5 is equal to 2y. I'm going to divide 2 from both sides, and while I do that, I'm just going to switch sides because I like to have the y on the other side. So y is equal to x minus 5 over 2. And now, that is the inverse function. F inverse of x is x minus 5 over 2. So how did we do that? We replaced f of x with y. We then swapped x and y. We then solved for y, and then replaced that with f inverse of x, because we now have our inverse function. Well, let's test it out. Don't just believe me when I say that. Let's see what happens if I do that. I'm going to call it, wow. I was going to call that something, but that marker is not writing anything. Sad thing is that marker looks really new. Nothing off of that marker. So it's garbage. So I'm going to call this g of x, just to make it easier than having to write this f inverse of x on here. So now I can say f of g of x is equal to, plug in x minus 5 over 2 for x, so 2 times x minus 5 over 2 plus 5 is equal to, when I multiply that through, to the 2's to cancel out, so I have x minus 5 plus 5 is equal to x. So far so good, that one worked. And if I take g of f of x, now I'm going to take 2x plus 5 and substitute that in for x there. So 2x plus 5 minus 5 over 2. 2x plus 5 minus 5, the 5's cancel out, gives me 2x over 2. 2 divided by 2 is 1, gives me x, and yes, they are inverses. So that's how we can find our inverse, and then how we can verify that we actually have inverses. What if I have a functional graph, or a graph of a function? How can I find the inverse of that? So let's say I have this. I'm going to give myself a grid. Try to make it somewhat straight. It's not, but just pretend that it is. Remember, always number those grids. Okay, so I've got my grid here. And what if I have this function? And I've got to be careful with that because I need to make sure that is never actually horizontal. It's just a really small slope. Okay, so I have this function. How do I find the inverse of that? So let's say I put arrows on there and call this f of x. Well, the cool thing with inverse functions is that graphically they reflect over the line y equals x. So that's my line y equals x. So the inverse function is just going to be a reflection over that. I can see that I've got this point here, so I'm going to make that point there. I see that at -4, 0, I cross over. So I'm going to come over here to 0, -4, and crosses over there. And so we are coming in, something like that, up, into there, coming close to and not quite hitting. We're getting it more into there. And we have F inverse of x. So when we're graphing, we can just reflect over the line y equals x. So let me just note that this here is y equal to x, or the identity function. So if we reflect over that, we get the inverse. Another thing that we can look at, drop my eraser, okay, is what did we do when we had a function and we wanted to find the inverse? We swapped x and y and then we solved, right? So if we have a set of data points that are part of a function, -2, 5, 3, 1, 4, 9, 5, 7, and 6, -3. Okay, first of all, let's verify it's a function. -2, 3, 4, 5, 6. I never repeated an x value, and I've got 5, 1, 9, 7, -3. I never repeated a y value, so it is a function, and it is 1 to 1. Therefore, it can't have an inverse. So the inverse of this function, we just swap x and y. 5, -2. 1, 3. 9, 4. 7, 5. -3, 6. And that is the inverse of that function. So we're just swapping x and y values, which makes sense considering how did we find the inverse function? We swapped x and y values, then we solved for y to turn it into a function. But that's really all we need to do to convert a function to its inverse. And we can see that it puts us back to where we were. We started with -2 and it gave us a 5. We started with a 5, it takes us back to -2. We started with 3, it gave us a 1. We start with 1, it takes us back to 3, etc. So that works pretty well. Okay, so let's try another example. I'm going to do red here. And deal with a rational function. So if I have f of x is equal to -3x plus 1 over x minus 5, where obviously x cannot be equal to 5, right? I can't have the denominator equal to 0. So we have a restriction on our domain. Now we want to find the inverse of this function. Well, we're going to do the same thing that we did on the previous example where we found the inverse from it. We're just going to turn this into y. Y is equal to -3x plus 1 over x minus 5. Then we're going to swap x and y. X is equal to -3y plus 1 over y minus 5. We need to solve for y, so I'm going to bring this y over to the other side. So multiply both sides by y minus 5 gives us y minus 5 times x is equal to -3y plus 1. I'm going to distribute x through. xy minus 5x is equal to negative 3y plus 1. I want to get this y by itself, and so I'm going to combine like terms here, right? I've got this xy and I've got this negative 3y over here, so I'm going to add 3y to both sides. Xy plus 3y is equal to, I'm going to get this 5x over there, so I'm going to add 5x to both sides, is equal to 5x plus 1. Trying to get y by itself, well, I have a common factor here of y, so y times x plus 3 is equal to 5x plus 1, and now I can divide both sides by x plus 3, so y is equal to 5x plus 1 over x plus 3, so the inverse function, f inverse of x, is equal to 5x plus 1 over x plus 3, just barely fitting it on the board there. So I have my inverse function, and notice that the inverse function has a restriction: x cannot be equal to negative 3. So the original function had a restriction on the domain, x not equal to 5. The inverse function has a restriction on the domain, x not equal to negative 3. And here's where I tell you the kicker. Because we swapped x and y to get the inverse function from the regular function, the range of the function is the domain of the inverse function. And the domain of the original function is the range of the inverse function. So, if I want to know the domain of this function f of x, that range is that y cannot be equal to negative 3. And if I want to know the range of my inverse function, that range is that y cannot be equal to 5. So basically what we're saying is that the domain and range of the original function become the range and domain of the inverse function. They just swap places. Whatever cannot be an input to the function cannot be an output of the inverse. And whatever cannot be the output of the original function cannot be the input of the inverse. So that's dealing with rationals, and we got to see how the domain and range work. So sometimes we can tell the domain and range from just looking at the function, and then that will tell us the domain and range for the inverse function. Other times it's really easy to tell the domain of the function, but hard to tell the range. So we can find the inverse, and then we can tell the domain, and then just use them to find the ranges of each one. So that's kind of fun. So we can work our way through these and find the inverse functions of a function, even a rational function. Just fighting with that board a little bit. So there we go. So let's look at another example. Let's say we have f of x is equal to x squared plus 4. Now, if we have this function, we should already see this is not a one-to-one function because we have x squared involved with this. So basically, we do need a restriction on this function, and that is that x cannot be, we'll just say that x must be greater than 0. Right? It can't be negative because if it's negative, then it's going to give us the same result as the positive. So we have this restriction that x must be greater than 0. So we want to find the inverse of this function. Y is equal to x squared plus 4. Change x and y. X is equal to y squared plus 4. Solving for y, subtract 4 from both sides. X minus 4 is equal to y squared. We take the square root of both sides. And y is equal to the square root of x minus 4. And we would normally say plus and minus. Right? When we take the square root of that, we're going to take plus or minus. Now, obviously, that's a problem, because if we allow it to be plus or minus, then x has 2 possible outputs. So we're going to eliminate that. So y is equal to the square root of x minus 4. But now we notice that this function, the f inverse of x, has its own restriction. X must be greater than or equal to 4. So let's put that x square root of x minus 4, and we see that the domain there, x must be greater than or equal to 4, because if it goes any lower than that, we end up with a negative. Now, having that in place and knowing that the domain of one is the range of the other, we can say the range of the original function is x greater than or equal to 4, and that the range of the inverse function is x greater than 0. So we do the work the same, we just have to watch and be careful about how we do this. We had a restricted domain here that stopped us from going negative on that. That's what made it a one-to-one function. And then here we had a restriction that stopped this from going negative, which kept it from going imaginary, and the two combined to give us this different domain and range. So, I just want to go into one more thing of this, and it's actually an application of inverse functions. And that application is cryptography. Cryptography is the science of encoding, encryption, decryption, cryptography, okay? So it's the science of encoding and decoding. So how does this apply to cryptography? Well, very simply, let's use the function f of x is equal to 2x minus 5. So we have this function. We came up with this function. And we want to start with something very simple. And we say, okay, a is equal to 1, b is equal to 2, c is equal to 3, d is equal to 4, etc., etc. So basically we're going to take the alphabet and assign each letter a number in a very simple format, A, B, C, D, E, 1, 2, 3, 4, 5, right? And that's not a very difficult decryption to do that. You probably did that as a kid. You numbered the letters, and then you were able to write a message in code, and then somebody else was able to look at that and take the numbers and convert them back to the letters. But that's a very simple form of cryptography. then what you did was you said, okay, rather than doing that, we're going to start at a certain value. And so instead of using 1, 2, 3, 4, 5, maybe you start at 16 and then do yours from there. And then the person has to know that it starts at 16 so they can decrypt it. And you could even do a rotating thing at that where you're starting 1 at the letter Q and rotating around so that P is the number 26. So with this here, now we can use this function to encrypt a message. If I plug in 1, you get 2 times 1 is 2, minus 5 is -3. So our output would be -3. So f of 1 is -3. F of 2 is 2 times 2 is 4, minus is -1. Right? So we can do that. You could even say that f of A is equal to -3. F of B is equal to -1. Right? So we have this encryption. The question is, when you get something like this, how do you decrypt the message? Well, you decrypt the message by having the inverse function. If you know that the function that was used to encrypt this message is 2x minus 5, then find the inverse. So that we can look at that as y equal to 2x minus 5, x equals 2y minus 5, x plus 5 is equal to 2x, equal to 2y. Y is equal to x plus 5 over 2. So f inverse of x is equal to x plus 5 over 2. So now we have our function to decrypt the code. So I'm going to put that right here. F inverse of x is equal to x plus 5 over 2. So I have my ability to decrypt. So now we have this code, this encoded message. 11, -3, 39, 5, -3, 23, 13, 1, 5, 41, 5, 5, 17, 5, 23, 3. So now we have this encoded message that came from using a equal to 1, b equal to 2, c equal to 3, d equal to 4, and the function f of x is equal to 2x minus 5 to create each of these. So I'm going to leave it to you as the end of 4.1 inverse functions to decrypt this message and see what it says.